Okay, good morning, everyone. So let's continue on with the chapter on momentum, and we'll probably finish this off today, and hopefully we can make a start on the last part of the course, which is thermodynamic stuff. Okay, so let me just start off by just going back to this slide. So last lecture I got a bit confused with what variables were, how they were defined. Turns out that whatever I said was correct. So what I just couldn't quite remember from just looking at this slide was how delta T was defined. So I went back to the textbook, and if you have a look at that, then the way they define delta T here is just some time interval, right? So that's sort of some time interval containing several of these pulses. So basically what we're trying to do here is to work out what the average force here is. And then this little n here is just the number of projectiles hitting it within that time interval. Okay, so this n over t means, say, in this case, little n is 6 here, and delta t is this period. So basically, whatever I said last time was fine. It's just that I think I called this delta t big T or something when I wrote that on the board. But otherwise, everything is fine. Basically, how all this stuff works is that if you calculate like the total impulse, what we're trying to do is calculate average force. So calculate the total impulse, say, within some time period. That's the area under the graph of these 6 pulses. So you could either integrate it, or you could simply measure the total momentum change of these particles, because of Newton's third law, these forces are equal and opposite. So you could either calculate the area under the graph, which is quite difficult, or you could just simply look at the momentum change of the projectile. And so that's the easier way to do it. And then the total impulse is just, of course, the number of these things, So if you've got 6 pulses, then it's like 6 units of the delta P. That's the total impulse. And then the average force is just that divided by the time interval that we're talking about, which is this delta T. So now I've marked it properly in the slides. I guess I'll update the slides in Brightspace. And then so we can calculate the average force in this way. So this is actually a little bit of a template example. Actually, we'll come back to this in the thermodynamics chapter, because when we look at things like pressure and things like that, this is more or less how you actually calculate it, by thinking of all the molecules in the gas actually hitting the sides of the wall. Okay, so we did that. We went through conservation and momentum. So if we calculate the total momentum of a system, then it's conserved, so long that there's no external forces acting on the system. So you have to remember that it's a thing that's limited to a kind of a closed system. So these things can hit each other and exchange momentum, and there could be forces between these guys, but then from the outside there should be no forces, and then in that case momentum is conserved. So momentum is it's a vector quantity, so we can look at each of the components separately. This is what I just said before, and energy is often not conserved in the sense of mechanical energy is not conserved. Perhaps I should write mechanical energy here just to emphasize that, mainly because there's other forms of energy like heat and sound the energy can leak into, but momentum, there's less types of momentum, if you like. So momentum is usually always conserved. We started doing elastic and inelastic collisions. This just basically means when either kinetic energy is conserved or it's not conserved. So in inelastic collisions, only momentum is conserved. So in such collisions, inelastic collisions, you just use your conservation of momentum. And for example, if you got 3 known velocities, then you could work out the 4th one from conservation of momentum. Completely inelastic collisions is a special case where the final velocity of the 2 objects are the same because they basically stick together at some point. So if you look at the motion of the center of mass, it's in a completely inelastic collision, it's unchanged. So if you actually draw a line back from after it's stuck together, then that would actually be the motion of the center of mass. And yeah, and where we got up to, I think, was talking about elastic collisions, and by doing a little bit of algebra, it's a little bit tedious, but you can actually work out now 2 velocities instead of 1, because basically now we've got 2 equations, right? So if you've got the initial and final velocities, this is in 1 dimension, by the way. So if you've got the initial velocities of the 2 particles, because we've got 2 equations and then 2 unknowns, the 2 unknowns being the final velocity of particle 1 and particle 2, then we can actually work out both of them in this elastic case because we've got 2 equations. In the inelastic case, we could only really work out one of those. So you'd have to have the other one given to you. So this is the relationship between the final velocities and the initial velocities, something like this. Okay, so I think what we did was just to derive those equations. So let's have a closer look at these equations and see what we can predict for them. So it's often useful, like in physics, to say you derive some formula. A common thing that you tend to always do is look in the limiting cases, because the general case is often kind of pretty complicated, as sort of is in this example. I mean, you've got these factors of masses like this. It's not totally obvious by looking at this formula what kind of the basic behavior is. So it often helps to look in some limiting cases. So these are things like the kind of thing that you often do is to look at cases where the masses are, say, equal, or in this case, say one mass is much bigger than the other one. And let's see what the formulas predict, and let's see if it makes sense. That's the kind of thing that you often do. So before plugging it into the formula, maybe what we can do is just sort of make some guesses, or see what our intuition is just from everyday kind of experience. So let's just take a few guesses at what would happen in these cases, and suppose these are elastic collisions, so that basically these are you can maybe think of them like as billiard balls, as I've drawn here, or in this case like a bowling ball and a ping pong ball. Okay, so in the case when you got one ball hitting another, and this is one-dimensional, so you don't have to think about the that it's hitting on an angle or something. So think of it like the white ball hitting the other ball, like dead on, right? So what do you think happens in this case? So if you hit the white billiard ball against the 8 ball here, dead on, what normally happens? Take a guess. Carter?
And then when you're hitting them, the white one hits the 8 ball, and the white one just stops, and the motion uses the black one.
Right, okay, yep. All right, so we'll mark that one down as the prediction for the first one. All right, what about the second one? You've got a ping pong ball, and it's going to hit a bowling ball. What do you think happens in this case? Right, yes. Exactly, yes. Okay, so we'll mark that one down like that. And then what about the third one? Bowling ball comes along and hits a ping pong ball. Stationary ping pong ball. Okay, all right. Everybody happy with those predictions? All right, so if we plug it in, so well, let's have a look, see what the formulas are. All right, so V1F, M1 minus M2, M1 plus M2, V1I, V2I, right? Okay, so say in the case of M1 equals M2, so in this case, let's say this is the white ball, and then this is the 8 ball, right? So the 8 ball is going to be, say, 0, and what this one would predict is that because M1 is equal to M2, this one would be equal to 0. So that's basically saying that the white ball stops. And then V2F, this one is going to be the other way around. So 2, 1, M, M1 plus M2, V1I, M2 minus M1, V2I. Okay, so in this case, sorry, not in this case, this is what the 8 ball is going to do. This V2I was 0, right? And in this case, this is the initial velocity of originally, that's the white ball. And in this case, these are the same. So it's like 2m over 2m and VI. So basically what this says is that the black ball will move at the velocity of the white ball, and then the white ball stops. So prediction was correct. Okay, great. Now let's do the other case. So in this case, the M2 is much bigger than M1, right? So this is, in this case, this is the bowling ball, and this is the ping pong. Okay, and then because M2 is much bigger than M1, basically in these factors here, this factor here is basically like a -1, okay? And in this factor here, because M2 is much bigger than M1, this M1 here is almost nothing. And then so this factor is sort of like 2, okay? So what we'd find is that, but then this one is basically 0 because this one was not moving, yeah? And this one is not moving. So basically minus VI, and the final velocity of V2 is M2, right. So M2 is much bigger than M1. So this one is basically going to go to 0, and this one's 0. Okay, so this one, again, the prediction is right. Now let's do the final case. So in this case, well, the way I've written it, it's like that. Well, let's how should we do this? Okay, so in this case, so one is the, say, the ping pong. Okay. Well, let's keep it to how I did it this time. How I did it on the slide here. So in this case, M1 is, okay, so M1 is the bowling ball. So this is the bowling ball, and this is the ping pong ball. And this V2, the ping pong ball is initially not moving, so we can, again, forget about these guys again. And then, in this case, M1 is much bigger than M2. So this factor is basically 1. That stuff there is basically 1 because M2 is very small. And in this case, this factor here is basically 2. So what happens is that V1F is equal to V1I, and then this is 2V1I. So what this is saying is that the bowling ball, the initial velocity of the bowling ball is the same as the final velocity. That kind of makes sense, you know, you've got this giant bowling ball, there's a ping pong ball, it doesn't even feel it just keeps on going, right? But this is interesting. The ping pong ball, the final velocity of the ping pong ball is actually twice the initial velocity of the bowling ball. So to me, that's not really necessarily really intuitive. I can see that, you know, that when the bowling ball's rolling along, it'll hit the ping pong ball. It might bounce, right? But I wouldn't have guessed it's exactly twice that velocity, right? But, well, sometimes you get things which are not exactly according to what you might have thought. So certainly, you know, there's nothing that looks strange here, but you wouldn't have expected that it's exactly twice, right? But under this elastic collision case, that is what happens. Okay. So, yeah. Any question? Okay. So then let's try this one. What is the final linear momentum of the target in this figure here? So this figure here, what's happening is this thing's initially 0. It's coming along with some velocity. Then afterwards moves something like this. If the initial linear momentum of the projectile is 6 kilograms per meter per second, and the final linear momentum of the projectile is 2. Okay. All right. So if the initial is 6, and I assume that they mean, momentum of the projectile, so meaning the thing that was moving originally. So basically V1F. So initial momentum is 6, and then the final momentum is 2. So yeah, final momentum of the target. So basically, what is the final momentum of V2 here? All right, so in the case of A, what is it? I don't think this is a trick question. So far, at least. No? Yes. See, told you, no, not a trick question. So initial momentum is 6, because that's 6, that's 0, and we're told that's 2, right? So that's 4. Okay, so what if this one was minus 2? Yes, 8. So plus 8 minus 2 adds to 6, initial 6. Okay, and then what is the final kinetic energy of the target if the initial and final kinetic energies of the projectile are 5 joules and 2 joules? So initially this is 5 joules, this is 2 joules. Initially this is stationary, so what must be the energy of this guy here? Yeah, 3, yeah. So just conservation of momentum and energy. Okay, so this elastic collisions case, that was just a one-dimensional example. But of course we can go to 2 dimensions or 3 dimensions. And in the case, well, of all collisions, momentum is always conserved. So in a, say, 3-dimensional case, there's actually 3 equations for conservation of momentum. So you look at the x component, the y component, the z component, all 3 obey conservation of momentum. So it's sort of, it looks like one equation, but actually it's 3 in the case of 3 dimensions. Now, depending on whether it's elastic or inelastic, it will be, there will be either, there will be also a kinetic energy conservation equation that looks like this. So, but that's a scalar equation, so there's actually only one more equation actually. So you either will have, 4 equations or 3 equations, depending on whether it's elastic or inelastic. So a nice trick to simplify the analysis is to use the freedom of your coordinates, because say you have some process like this. So you've got, say, initially stationary object here, and then the object is coming in moving. So just like in a billiard, snooker, pool. It hits it, white ball goes here, the other ball goes this way. Now, so I said that, momentum is conserved, and, we have 3 equations, or maybe in this case, 2 equations really, because, it's a 2-dimensional example. So so it's two equations. So the x and y components are separately satisfied, but what we call the x direction and y direction is up to us. We could choose it in any angle that we like. So just to make our lives easier, we might as well choose it in a way such as to simplify the problem as much as possible. So if we choose the x and y coordinates like this actually makes our lives much easier, because so if we align the x direction along the movement of the original ball, and then basically what that does is to make the y direction, like the momentum in the y direction, initially 0. Yeah, because initially this is not moving, and if we align the x-axis this way, then the y direction, there's no movement in the y direction. The velocity in the y direction is 0. So that means that if the velocity of all the objects, the the component of the velocity is all 0, then all the momentum is 0. So the initial momentum is just going to be 0 here, right? And then, of course, afterwards it bounces off, and there will be some momentum in the y direction of each of these balls. Say this one, it's going to be moving, say, at an angle theta 2, and then so if you just use trigonometry to work out what the y component is, it's just the momentum, which is m2v2f times sine theta. So that's the momentum of that one. This is the momentum of the other particle, but it's moving in the opposite direction, so we've got a minus sign. So these two things, of course, have to add to 0. Right? For the x component, well, there's movement in the x direction, so that's the initial momentum. But we don't, good thing about aligning it with the movement is that we don't have to put any sign factors or anything. It's already in that direction. So we don't have to worry about that. We just put m1v1 initial. And then the final momenta, well, they both go in this positive x direction, so they both got a positive sign, and then these are just cosine factors instead of sine factors. So that certainly makes life a lot easier. Okay, so let's use that trick and look at this question. So in this figure, same setup. Suppose that the projectile has an initial momentum of 6 kilograms meters per second, a final x component momentum of 4 kilograms meter per second. So this ball now deviates, goes this way. The x component is 4. A final y component momentum of -3. It's going down. For the target, what then are the final x component momentum and the final y component? Okay, so let's start with the x component. So what's the final x component of that ball going to be? Yes, 2. Because the initial x is 6. The final x of this one is 4. So they have to add it to 6. So 4 plus 2 is 6. Okay, what about the final y component of this ball here? Yeah, 3, because the initial y is 0, right? It's moving along the x-axis. There's no y component. So this is minus 3 in the sense it's going down. So this has to be plus 3. Okay, so that concludes that chapter. Any questions on this chapter or anything that's appeared up to now? Okay, if not, then we will move on. Okay, so this is a totally different topic, thermodynamics. So, well, we're going to start with talking about some basics like temperature and heat, so forth. But yeah, I mean, just generally this kind of science is, I mean, I think heavily motivated by, you know, the innovations in sort of engineering and things like that. So you're going to see a lot of stuff like, you know, these pistons and work and all these kinds of things. And I think ultimately a lot of the motivation and the importance of this topic is kind of coming from, you know, people invented engines to do certain things, and well, engines are pretty magical kind of things, really. You know, you just heat something up or you put some fuel in, and then, you know, they just go and actually do some work for you, right? So it almost seems kind of like magic, right? So I think people wanted to really understand this and understand, you know, how is it kind of possible that we're actually getting these machines to do work for us when for millennia we had to, you know, break our backs, you know, doing farming and all these kinds of things. So, so yeah, I mean, what we're going to basically do in this chapter is just sort of these basic ideas of thermodynamics, but eventually we'll cover sort of ideas like, you know, the Second Law of Thermodynamics and entropy and these kinds of ideas, which are actually pretty interesting ideas and even have applications to other areas. So there's ideas of entropy actually relate even to areas like information theory and you know, so the basic unit of information, for example, is entropy, and even in quantum mechanics you start to use these types of ideas eventually. So there's a lot of fundamental kind of ideas here. Okay, but starting with some basics, I think everybody knows what temperature is. Basically, you know, it's roughly speaking a measure of how hot or cold something is. The usual units that we will use are kelvins, and Kelvin scale has a absolute zero, a temperature where you cannot, basically there's no lower temperature than absolute zero. Eventually, because this is related to the motion or the energy of the underlying atoms, right? So what we'll see eventually is that temperature really is actually a measure of how much kinetic energy, in fact, the atoms possess. So of course, if the atoms stop, then there's no more there's nothing lower that you can no lower temperature that you can go. On the other hand, there is no real maximum temperature. There's like, you know, in the same way that there's no real well, I was about to say there's not really an upper limit to the kinetic energy, but I suppose there is. I suppose, well, okay, it depends on if you think classically or not, but so if you don't take into account any relativity or anything like that, then obviously there's no upper limit to velocity, but I think there's no upper limit to the energy something can have. And yeah, so if you take into account relativity, then you'd have to use relativistic formulas for the energy, and then there would be no upper limit. So unlike the classical formula for the kinetic energy, where the speed of light would be the upper limit, I think there would be no upper limit to the energy, and then hence there's no real upper limit to the temperature. What we're going to first start off with is the so-called Zeroth Law of Thermodynamics. So before just talking about this, we need to introduce a thing called a thermoscope. Basically, thermoscope is a uncalibrated thermometer. So it's basically something that tells you whether something has a high or low temperature. So such things are actually not so hard to make. So of course, you can have thermometers made of all kinds of things. The traditional thing is to have some liquid in a glass container, and then looking at the expansion of it, you can see basically how hot or cold something is. But you can also have electronic devices that measure temperature, because again, the temperature is related to the resistance of an object. So if you measure the resistance, you can kind of work out what the temperature is. But let's not worry too much about how you would make such a device. In fact, we'll talk about something like this in a minute. But it's basically something that tells you whether it's high or low, and then basically these units, just think of it as completely uncalibrated. So it gives you some number, but it's nothing related to kelvins or Celsius or anything like that. Okay, so we've got such a device. Okay, so given that you got such a device, then you can basically figure out how hot or cold something is, right? Now, so the Zeroth Law of Thermodynamics is stated like this. So if bodies A and B are each in thermal equilibrium with a third body T, then A and B are in thermal equilibrium with each other. So basically what this is saying is something like this. So, thermal equilibrium basically means that the two objects are at the same temperature. Okay, we can just work with that definition. So, the thermoscope itself has some temperature, of course, but suppose it's you leave it for a long time, and so everything's all the same temperature. So then you bring your thermoscope in and you measure the temperature of the first object, and then you find it's 137.04. Then you go and measure the temperature of the second object. You also find it's 137.04. Then basically the Zeroth Law of Thermodynamics states that this implies that A and B are also in thermal equilibrium with each other. So basically there would be there will be no energy flow between A and B so long that they're at the same temperature. So this might look like a kind of almost obvious statement, and indeed it was kind of obvious to people researching thermodynamics hundreds of years ago. And so this is why it's called the Zeroth Law of Thermodynamics. It's sort of an afterthought. But people realized sort of later on that, they made a first law of thermodynamics, second law, and so forth. And then they realized, actually, this is actually a pretty fundamental assumption that we actually all made without really realizing that it was really an assumption. So just to make everything consistent, I guess people introduced a zeroth law as a kind of a more fundamental thing. But what's really the point of this? The point is really that this means that you can define something that's a measure of temperature, and it really can be something that is calibrated. So we sort of take for granted that, okay, there's something that's a temperature because, of course, our bodies feel heat, right? Or if it's cold. So, we have an inbuilt sense of something is hot or cold. So, this is why, in a sense, for us humans, this is quite an obvious statement, because basically it's saying that, stuff is either hot or cold, and if I think it's hot, then you're going to think it's hot too, because hotness is a kind of an intrinsic fact of nature, right? But, everybody knows. Kids know this, so you don't have to go and, scientists, had to really think that, actually, this is not really necessarily so obvious. So essentially, it's a statement that saying that, well, temperature is something that, temperature is a thing, okay, and it can be quantified, and you can put a number on it. So I think I've already explained it, but this is my silly example to say that, well, it doesn't necessarily have to be that way. It could be a rather subjective thing. For example, this is a very subjective kind of thing. If say this is the guy that's sort of like the thermometer, and then this is the other two objects, like A and B here, right? Analogies, right? And then so, this guy would perceive this person to be a very nice person, and so he would give them a score of 5 out of 5 for friendship level. He would also think that this is a very nice person, give them a score of 5 out of 5, but that doesn't necessarily mean that these guys are going to get along or give a score of 5 out of 5 at all. So, well, this is a very subjective, how you perceive somebody, in terms of whether you like them is a rather subjective thing, but temperature is not. Temperature is a kind of an objective quantity that you actually can measure. Okay, so if we've established that temperature is something that you can actually measure and quantify, then let's go ahead and try and quantify that. And so what we're going to try and do now is to sort of think from first principles of how you might actually quantify temperature in a imagining that you didn't have any thermometers or anything like that. So say you were the first person to realize that, temperature is something you can quantify. Okay, so let's make up a scale for it, and I'm going to name it after myself. So suppose you had that task, then you'd have to know that there's such thing as absolute zero. So that's okay. It's a little bit of a cheat, but okay. So let's go with that assumption. So if you knew that there's such a thing as absolute zero, so let's call that zero. Now we need another calibration point, and of course this is not historically how it was done. It was worked out through many different iterations, but a very nice another calibration point that you could use is the so-called triple point of water, and the reason why is because this actually gives a unique value of the temperature. So, if you defined your temperature scale so that, say 100 degrees that's when water boils. So the problem with that is that people living on different altitudes, if you're on high mountain or something, then you'd actually get different temperatures because water boils at lower temperatures if you're at a lower pressure, right? So that's not really a great way to calibrate temperature because that's going to depend upon the pressure, of where you live, or even the particular day that you happen to be measuring it from. But if you wanted to, take out this pressure dependence, then what you can do is you can look at this triple point, because this actually takes the pressure out of the equation completely, because there's only one unique temperature and pressure where you can have a solid, liquid, and vapor all at the same time. And so this is basically what the triple point means. It's a special point in this phase diagram of temperature and pressure of water where you can, you have ice, liquid water, and water, gas, steam, all at the same time. And that's a kind of a unique signature that you can use in order to calibrate your temperature. So you have to have pure water and stuff like that. Okay, so what you might do is you basically first get some kind of glass thing here, put water in it, and then you adjust your temperature and pressure so that you get this triple point, right? So you have to adjust the pressure here, so you're going to be letting in the vapor, adjusting it so that you have exactly this condition, basically ice, vapor, and water, liquid water all at the same time. And then once you've got that gives you your sort of temperature reference, right? Because that only happens at a particular temperature. So what we're going to do is, in terms of kelvins, then this actually has a temperature of 273.16. Okay, and then if you want to, so that actually gives us two reference points in order to make a calibrated definition of temperature. So the 2 points are this absolute zero and this triple point water. And then once you've got 2 points, then basically you can evenly divide your scale between those 2 points, and then you've got your temperature scale. So so what are we going to use as our kind of thermometer? So what you can do is, for example, you can have a so-called constant volume thermometer. And conceptually what this thing is so what is it really? It looks something like this. It's basically some gas-filled bulb here. And what we're trying to do is measure the temperature of this surrounding. So suppose you got your water bath here at some temperature. That's the temperature that you're trying to measure. So when you're trying to calibrate it, what you might do is instead fill it or surround it by this glass container, which is at the triple point. But more generally, if you're trying to measure the temperature of something, then you're dunking it in this bath here, and then it's got some kind of gas in it. And here's some mercury. And this side is open, this side is, completely closed. And basically what this contraption does is to compare the pressure of the inside here, inside the gas-filled bulb, compare that with the ambient pressure. And the way this works is that so in that tube here, well, so it's like this. Okay, for all the rest of it. So this is the mercury, and there's some, well, okay. We can think of some force being applied due to atmospheric pressure. And this will be equal to P0 times by the area. And that this area is the cross-sectional area of this tube. So that's the force on this side. And basically that force must be balanced by the pressure that's acting on this side. So this is the sort of the atmospheric pressure. This is the force for gas. So we've got some different pressure, A. And there's also the weight of the mercury here in this side. And this force that's acting over here would be equal to the force of the gas plus this weight of the mercury. And the weight of the mercury is, so this is the density of the mercury times by we need the volume of this column here, and the volume of the column is AH. And these two things basically all have to be equal to each other because basically, well, you know, these forces on either side, they balance. So this force at this point here has to be equal to this force over here. So basically what we have is PA plus rho AH has to be equal to P0 A. All these A's actually cancel. And sorry, I missed a factor of G here. So this is mass per unit volume, and then so that would be the mass, and then it's mass times G is the force, right? Sorry. And then so the pressure that's actually here is actually equal to P0 minus rho GH. Because we've got it there. Okay, so this basically gives us a way of actually measuring the pressure that's inside this bulb here. So this bulb here has some pressure, and well, it's relative to atmospheric pressure, but you can measure the pressure basically by looking at how unbalanced the the positions of the mercury columns are. Okay, so what we're trying to do here is essentially we are kind of converting pressure into temperature. Okay, so basically the hotter something is, the more pressure it is going to experience. Yeah. So you can imagine if you got a can of something and then you throw it in the fire, it will explode because basically the pressure will build up and then it would explode at some point. So we're kind of implying what the temperature is from the pressure. And so we're going to use this kind of device in order to convert our pressure into temperature. And there's some proportionality constant here, C, which is basically the calibration effect, right? So whatever we're going to measure, we get some value of the pressure here, but we need to actually know what this calibration here, C, is. So this is why we need the points to calibrate it. So we've got the 0 and the 273. So if we were trying to derive a Kelvin scale, so if we were basically using this to try and work out how many kelvins something is, then what we do is, we've basically defined the temperature at this triple point. So in this case, we dunk the thing in the triple point of water, measure the pressure at that point, and then define that to be 273.16, right? Okay. Because we're making a Kelvin scale thermometer. That gives us some constant here, which in this case it's going to be 273.16 divided by P3. P3 is whatever value of the pressure that you actually you just measured when you did the triple point. Okay, so this is how you would make a sort of a constant volume thermometer. Oh yes.
I'm actually curious, why is Kelvin being set to 273.16 and not 0.15?
Oh, because this is, I think, the triple point, right?
Okay.
Yeah, so because we're using the triple point as the calibration point, so it's not the...
It's just not at like Celsius is equal to 0, it's at the... I'll just compare it.
Yeah, like you need to actually adjust the pressure a bit in order to see the triple point. Like, so at regular atmospheric pressure, you're not going to see ice, steam, and water all at the same time. So I think if you look here, this is
just ever so slightly.
yeah, this is 1 atmosphere here, right?
Yeah.
So this is like actually way below. This is like less than 10 millibars. So it's actually quite low pressure. Yeah. 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 Okay, so all right. So this gives us a way of kind of making a thermometer from scratch, but still some more problems. Like, so if you do this, you get a reasonable kind of thermometer, but what you'd find is that depending on the type of gas that you use and the amount of gas that you use, you will start to get kind of different values that don't quite agree with each other. So what this graph is showing is, say this is like the pressure value that you actually measure, but basically maybe the way to think of this is just like how much volume of gas that you actually used in here. So did you use a big bulb or a small bulb, so forth, right? And then this is obviously using different types of gases. Now, what we're doing here is we've done this procedure here, and then we've dunked this in now boiling water, which is supposed to be, what is boiling water? It's 270. What is boiling water? 373 point. Well, do you remember? No. Okay. Right. Okay. So it's obviously, well, okay. So it's 373 point something. Okay, but if you use these different bulbs and different gases, then you'll get slightly different estimates. See, all these are 373 point something, but they're not quite the same. So, it's a bit of a problem if it kind of depends slightly upon what gas or what size bulb you actually happen to use. But what you notice here is actually, as long as you use a very, very small amount of the gas, actually all these agree. So, okay, well, either you use a tiny bulb, but, ideally you want a bulb so tiny it's zero, right? But if it's zero, then you can't even do the experiment. And, in fact, you'll probably run into all kinds of difficulties because of using a small bulb is experimentally not really very nice. So the kind of procedure that you might do is to instead use a small bulb, but then use increasingly small bulbs and then extrapolate down to zero. And then when you extrapolate using increasingly smaller bulbs, then you get your final estimate. And this way you can eliminate this issue with the size of the bulb and the type of the gas. Then, so we can define our temperature instead like this, where it's like 270.16 divided by P3, which is whatever the value that you get for your thing with the triple point calibration, and then the temperature is defined like this. Okay, so just to summarize, the procedure for making like kind of a robust thermometer from scratch would be something like this. So you fill the bulb with any gas, dunk the bulb into water triple point, measure the P3 for that amount of gas, and you get the pressure from that, from this formula that I've got here, that. So you're reading off the mercury measurements. And then put the bulb in whatever you're trying to measure, find the P, calculate this thing. Now take out some of the gas, and then do steps 2 to 4 a few times. And then draw a graph of T versus P3, a lot like this one. So you're going to get some data points like here, here, here. And then extrapolate down to 0, and then you've got your final value. Okay, well, I think, in a way, I don't know why they do this in the textbook exactly at this point, but I think this sort of teaches you a couple things about, this kind of gives you a little bit of a flavor of what people actually do in research, right? So when you're doing research and say your aim is to make a thermometer, you tend to sort of run into certain issues, and you might start with a kind of an idea of how to make a thermometer, but then you make it and you go, oh, okay, well, actually, there's a couple of issues here. Like, it basically works, but then there's a few sort of little bugs in it. Like, in this case, the bugs are things like, oh, what if you use a different gas, you get different values, or what if you use different size bulbs, you get different values, right? So this is basically, it's kind of an iterative process. You wouldn't have thought that you had to do this whole procedure to make a thermometer, but it's sort of like the first try gets you pretty much 90% there, and then the rest of the procedure is to fix up the bugs, and then in hindsight it looks completely weird. It's like you're doing some weird graphing, you're making different bulbs, and extrapolate. You wouldn't have thought that you'd have to do this, but then this is eventually the recipe that you need to do in order to get something that's actually robust and something that kind of anybody can do to get the same value, because really the point is that anybody can do this and then they get the same answer. And if you don't have that, then there's a bit of a problem, because we were trying to define a kind of universal scale that anybody can use. Okay. All right. So now back to some more kind of basic stuff. So I think everybody knows this. We can convert between various temperature scales, Celsius, Fahrenheit, so forth. Conversion formulas like this. basic point here is that all these scales are always linear scales, right? So nobody uses some kind of non-linear scale of temperature because, well, linear is the easiest way, right? Of course, you can conceive of some bizarre non-linear scale where, the hotter you go, maybe the temperature steps get smaller or bigger or something. But generally, nobody does that. So all temperature scales are basically linear. So they all just differ by basically some offset. So in the case of Celsius, it's actually 1 degree in kelvins is the same as 1 degree in Celsius. The amount of temperature change is the same. It's just that the whole thing's offset by this value because originally Celsius was defined, of course, with reference to the boiling point of water and the freezing point of water. So 0 and 100, right? And then people realized, actually, scientifically speaking, it makes more sense to define absolute zero as 0, right? Instead of some weird number like minus 273. Fahrenheit, okay, so this time the temperature increments are a bit different. So 1 degree in the Fahrenheit scale is actually, so it's a bit bigger than Celsius. So 1 degree in Fahrenheit is different to 1 degree in Celsius, and there's an offset too, but it's still a linear kind of thing. Okay, so given that temperature scales are all linear, so let's have a look at this question. The figure here shows 3 linear temperature scales with the freezing and boiling points of water indicated. So freezing point, so these are imaginary kind of made up temperature scales. So we've got temperature scale X and W and Y. This one is like minus 20 goes to 70 between freezing and boiling. 30, 20, 0, 90. Rank the degrees on these scales by the size greatest first. So, which has the largest, like 1 degree of these things? Which is the largest? And which is the smallest? Sorry? Yes, they're all the same, yeah. Because the temperature difference on these scales, this is 90, right? This is also 90, this is also 90. So they're all the same, yeah. The 1 degree on each of these scales is actually the same, a bit like Kelvin, Celsius. Rank the following in temperature highest first. 50 degrees X, 50 degrees W, 50 degrees Y. Which is the hottest on these scales? Right, yes, X, yes. And then? Right, Y, yeah, and then W. Yeah, I guess because 50 is the closest to the x, right? So this is further away, so it must be way down here, sort of in the middle. Yeah. Okay. All right. Well. Yeah. Well. Okay. Well, let me just add that. I mean, sometimes it's good to sort of also be able to write it down mathematically. So basically, what we can see from these relations is that the W scale is just offset by from the X scale by basically just adding 50, right? So we can write down an equation saying W is X plus 50, and we can also say that Y is X plus 20. So if we wanted to, we could also just use this then just to convert between all the different temperatures, right? So of course we could just sort of look at it and see it because it's almost obvious. But we can convert between these scales just by writing down the formula because obviously this means that X is equal to W minus 50, and then X is equal to Y minus 20. So 50 degrees W means actually 0 degrees on X, and then 50 degrees Y is actually 30 degrees X. And then once you convert it to the same scale, then it's obvious because it's all on the same scale. So we don't, okay, we can say, okay, so 50 degrees X is of course 50 degrees X. So this is highest, this is the lowest, this is the middle. Yeah. Okay, maybe we'll leave it there. And so could you leave your homeworks up here and I will collect them. We'll see you on Thursday.